Hello and welcome back to our energy unit. So far this unit we have talked a lot about, because remember we split this unit into two different types of sections. We first started talking about our energy with work and power, and then how that can be described as kinetic and potential energy. And then we started to break it down into wave behaviors with our mechanical waves, which mechanical waves move through a medium, so it needs either a solid, liquid, gas, or plasma to travel through. And then we started talking about how our protons, who have a positive charge, and our electrons, who have a negative charge, how they are the two that have opposite charges which attract, and that can cause that electrical current or a chemical reaction, which then can lead us into different types of radiation. And so the past couple of days we've been talking about how if you have electricity, you can create a magnetic field, and if you have a magnetic field, that can cause electricity, so they come hand in hand. And when you have smaller and closer distances, that increases the force. So now we're going to go back and look at the electromagnetic spectrum. And so I did share a handout with you guys that looks like this here. I would love, I would love for you to print this out and color it too. It will be a great reference for the test and quizzes, as well as the space unit. And then you might also want to get a sheet of paper out, because I'm going to talk about this today too. Clearly I would normally write this on the whiteboard, but we're going to talk about our Doppler effect again, and how that can be used in many different scenarios as well. But let's go ahead and first take notes. So in Canvas, logging into your class here, I'm going to go down to the energy unit, and we're looking for the notes that are called electromagnetic spectrum, and I abbreviated them with EM, so electromagnetic spectrum. And let me just download this for us here. So we've already really been discussing the electromagnetic spectrum quite a bit. We've talked about it with just how energy can move. Key terms that we are going to be discussing is frequency and wavelength, and then the kinetic and potential energy associated with some of these waves. So by the time you're done with today, tomorrow, and Friday, hopefully you'll feel pretty comfortable with looking at a certain way a wave looks like it does here on this first PowerPoint slide. And you'll be able to say, oh, well, this has a long wavelength, so therefore this is also going to have a low frequency. And if we look over on this side here, we can see that these have short waves, so therefore it has high frequency, and we should then be able to figure out what kind of energy it has. High energy, high frequency, short wavelength; low energy, long wavelength, low frequency. I think I said that correctly. So we're going to go through and kind of discuss like what some of these means, and then you'll actually end up doing a project here in a little bit on picking one of the different types of radiations and how it's used in our everyday lives. So let's go ahead and get started. So the electromagnetic spectrum is, I like to say, like, we're going to be talking about a rainbow today. We're going to be looking at Roy G. Biv and how red can be associated with certain types of wavelengths, and blue. Because part of the spectrum in the center part, right in the middle, you should be able to see that there is, let's see if I can get my bearings. There's visible light. And within the visible light, all the colors are broken down in the spectrum again. So meaning that we can see all colors, unless, unfortunately, if we're colorblind or lack some deficiency. But more than likely, most of us can see red, orange, yellow, green, blue, indigo, and violet. And that is part of the spectrum. And then there's other radiations that we can't see, such as a radio wave. You are receiving information through your Chromebook right now through a radio or microwave. Those have low frequencies, but you can't see them coming to your computer, or or if you've ever been exposed to the sun, you can feel your body warming up and getting that UV radiation, but you don't actually like feel the burn or see it coming from the sun. You can't look out into the atmosphere and be like, wow, it is super saturated with UV radiation today. So we're going to kind of talk about what this looks like. So it is in different types of forms, and it's also in the form of light, and I feel like that is probably the most confusing. So once again, this is thermodynamics, this is our radiation, and it can move through anything, so it does not need a medium. So electromagnetic spectrum is in the complete spectrum, and it is all forms of light. And the electromagnetic waves consist of electric and magnetic waves. So things that we've been talking about, and kind of the title of it should give it away too, is that they are electrically charged particles. And when they are electrically charged, they're oscillating and they're vibrating and they are creating a magnetic field. And some of them are going to have really high magnetic fields, gamma rays. Some of them are going to have very weak magnetic fields, radio waves, and we'll kind of talk about what that looks like as well. And once again, they're vibrating, so we have that idea that the energy is always moving, vibrating really, really fast at high frequencies or vibrating really, really slow at low frequencies. You don't have to get these down unless you really want to, but these are the different types of radiations that we'll talk about. So once again, I've got them broken down here on this chart. If I can bring it down for you. I'm not doing a very good job. And radio waves are normally associated with the red part of the spectrum, microwave orange, infrared yellow. Visible light's going to be all colors because once again we can see them all. UV is going to be green, X-ray, purple, and then gamma ray indigo. And once again, it goes from low energy to high energy. So radio waves, cell phone waves, microwaves, low, gamma rays, you don't want to be associated with them. I know we've talked a little bit about the idea that this would be when gamma rays are released when a supernova happens, and we'll talk about that a lot next unit, as well as they can be energy like that can be released when you have a nuclear disruption such as Chernobyl, when the power plant melted down. That released a whole bunch of radiation into the atmosphere. It's things you don't want to be around because too much of it can be really bad, especially in that high area, this here, UV, X-ray, and gamma. Here's just another picture, and kind of just once again to give you an idea. We're looking at frequency again, and remember that is in hertz. And you can see that we have our longer wavelengths associated with this side of our spectrum, radio, microwave, and infrared, low frequency, long wavelengths, low kinetic energy. Whereas over here, our X-ray, our UV, and our gamma, we have very short wavelengths, high energy, high frequency. So some of our equations are going to kind of come back and play. You just have to understand them. We're actually not going to plug any information in to find the frequency with the spectrum. We'll use that mostly just for when we were talking about mechanical waves, but make sure that you still know them. That's really important. They're going to be on the test and quiz. So properties of electromagnetic waves include speed, frequency, and wavelength. So once again, I'm going to show this picture here. So if we look at, I drew, and we're going to talk about the Doppler effect here at the end, but that's my really lame picture of an ambulance. And when an ambulance is moving towards someone, remember with the Doppler effect is that you get at high frequency, and so that's going to be this side of the spectrum here. Whereas as it passes you, it's low. Remember we watched the video with Sheldon, he was like, meow, going really slow, and as objects pass, it was and he was dressed up for Halloween as the Doppler effect. So frequency, wavelength, and speed. You can also think about speed, frequency, and wavelength in this format. Speed equals frequency times our wavelength. Remember, sometimes we were just using speed equals distance divided by time too. But this is the one that we're going to be using with our electromagnetic spectrum. So once again, if you think about it, if we're asked about the speed of our slow side over here with our red, orange, and yellow, our radio, our infrared, and our microwaves, we can just think about it. Well, looking at the wavelength, they're really long, and that should therefore just denote that we know it's going to have a lower frequency. So the speed's slower. Whereas on this side over here, where we have our short wavelengths with our UV, X-ray, and gamma, we're going to have then short wavelengths, which is going to make high frequencies. So that's going to mean high energy, so high speed. And then light. All light travels at a constant of 3 times 8 meters per second in a vacuum. Sorry, I had to think about that for a minute. I'm like, wait. So all light is traveling at 3.8 meters per second in a vacuum. So remember, that's not a Hoover vacuum or a vacuum that someone uses at your house. This is space. So there's no medium as light leaves the sun and travels to the earth. So it's moving at us at a rate of 3 times 10 to the 8th meters per second. But once it hits our atmosphere, then it changes into a medium. It's starting to move through gases, and as it gets closer and closer to the ozone, it even moves through denser gases. So the speed of that changes. But if you and we'll talk about this in the space unit, it actually only takes 8 minutes for light to leave the surface of the sun and travel to the earth. And that's actually pretty fast, knowing the distance, and we'll talk about what that distance is next unit. So relationship between wavelength and frequency, kind of already been talking about it a little bit with my picture here. So wavelength and frequency have indirect relationships, indirect. So in other words, wavelength increases, frequency is going to decrease. So if you have a long wavelength, you're going to have a low frequency. So once again, therefore wavelength and frequency have a indirect relationship. Long wavelength, low frequency. Short wavelength, high frequency. And there it is. Short wavelengths have high frequency. Long waves have low frequency. This is probably one of the most important things you could probably remember for the rest of this unit and into next, because we're going to talk quite a bit about some of these things. So once again, short wavelengths, high frequency. Long wavelengths, low frequency. There you go again. And I've kind of got it drawn there at the bottom. And I'm not going to get, this works much better on a whiteboard. There you go. Electromagnetic waves and energy, high frequency, high energy, low frequency, low energy. And once again, you can see I've got it kind of written there at the bottom. And you can see this on this one too. Once again, I think this would be something really beneficial to print out for yourself. And this is where I say that if you haven't already, sketch it somewhere. So pause this video, write it down in your notes, maybe even go ahead and let me put this up here too so that you can kind of see it as well. Might not be a bad idea. Make sure that you have R associated with red, radio waves, are O, orange microwave, yellow infrared, G for visible, B for UV, I for indigo, and V for violet with our gamma rays. And then also get down at the bottom, long wavelengths, low frequency, slow waves, short wavelength, high frequency, fast. So pause the video there if you need to. Oh, I forgot it was so interactive. Here's just another picture. You can see, to give an idea, about the frequencies and how fast they're moving. So radio waves are really, really, really high, and they're moving free throughout our environment everywhere. Whereas all of a sudden it starts to jump down pretty quick. Infrared